We need groceries from the store. Let's make a list. Let's get some bananas, apples, and carrots. We want to get 4 apples, 6 bananas, and 12 carrots. Here in week 1, at the store, the cashier places all the groceries in the bag after ringing up all of our items. Our total comes to $6.26. We take our food home, and during the week, we eat it all up. Now it's week 2, and we need to stock up again. This time, we decide to get 3 apples, 7 bananas, and only 6 carrots. At the store, our total comes out to be $4.94. Again, we take our food home and eat it all. For week 3, we decide we need 6 apples, 3 bananas, and no carrots. The total comes out to be $4.14. In summary, in week 1, we bought 4 apples, 6 bananas, and 12 carrots for $6.26. In week 2, we bought 3 apples, 7 bananas, and 6 carrots for $4.94. And in week 3, we bought 6 apples, 3 bananas, and no carrots for $4.14. Now obviously, when we're at the store, we can see the price for the individual items. For the sake of this video though, we're going to pretend we don't know the individual prices for 1 apple, 1 banana, and 1 carrot. We can represent the situation in the form of a matrix, which is just a list. If we take the coefficients, which is a fancy way of saying the amount of each item we bought, and put them inside brackets. We can also put the abbreviated names for each item in a 3x1 matrix or list, and the costs in a third matrix. Our goal now is to create what's called an upper triangular matrix. The purpose will become clear at the end, as well as this last little change to the matrix, which is a type of permutation that doesn't change anything about the situation, only reorders the list like so. An upper triangular matrix has a number in the first column of the first row, a number in the second column of the second row, and a number in the third column of the third row. Below each number, there should only be zeros. So you can see why I had to switch the first and third rows, because an upper triangular matrix cannot have a 0 in the third column of the third row. To start tackling this matrix, we're going to multiply the second row by 2 and subtract the first row. Whatever we do to the coefficient matrix, we must also do to the solutions matrix. Now, multiply row 3 by 6/4 and subtract row 1 from row 3. Then, multiply row 3 by 11/6 and subtract row 2 from row 3. Now technically, we're done turning this into an upper triangular matrix, but there's one more thing I like to do, which is divide the row by the leading coefficient. This means row 1 is divided by 6, row 2 is divided by 11, and row 3 is divided by 21. Side note here, I've rounded the decimal places for show, but the calculations I do will be based on the exact values I found. The power of this upper triangular matrix is shown by thinking about the equations it represents. Row 3 says that 0 times A plus 0 times B plus C approximately equals 19 cents. This means that the value of 1C, or 1 carat, is approximately 19 cents. Row 2 says that 0A plus B plus 1.09C equals 52 cents. Now that we know what the value of C is, we can plug it in and we get that B plus 1.09 times 19 cents equals approximately 52 cents. Rearranging this, we find that B equals 32 cents. Row 1 says that 1A plus 0.5B equals 69 cents, which is really saying that A plus 0.5 times 0.32 equals 69 cents. Which means that A equals 53 cents. To check that our values are correct, we can plug them back into our original equations, and we see that for each week, the total price matches what the individual prices add up to be.